Okay, so let's get into how collision and physics work in a game engine. So it's worth pointing out that what we're talking about is more or less simulated physics. It's not as accurate as the kinds of things that we might use to, say, predict the weather or um, simulate an explosion or something like that. Although we can do both of those kinds of things in the Unreal physics system, but the primary purpose of game physics is to be speedy and to look reasonably okay for the player. So it's all about the player's experience, really, rather than accuracy. It's also worth noting, too, that physics systems, in the case where they start to feel more realistic, probably came into being around Half-Life 2. That was one of the first games that really put that into play and turned it into puzzles. However, physics in some regard has existed the whole time, and we'll kind of take a look at the way we fall back to that. So it's worth considering that it's not always necessary to pull in the real kinds of physics. You can simulate these things simply by moving characters around over time. We've already seen that when we're moving our first-person character around, for instance, we're really only moving them. We're moving them according to a speed and a direction, but we're moving them according to our own rules and not physical rules necessarily, right? So it's not always necessary to boil down to physics, but it's certainly worth understanding how that works, and then when you may or may not want to use physics in your game. Okay, so recall our render loop, or our game engine loop here, where we have the player input, the logic update, and then the rendering. A standard physics simulation will really just do the simulation to presentation mode. Sometimes that will be in a loop, sometimes the presentation will be part of the physics simulation. In other cases, it'll just run the entire physics simulation almost as a complete render update, potentially store states, and then put the presentation on the output. This again would be something like your weather simulation. They won't actually care about trying to render, say, where the clouds are, where the rain might be in their prediction, because they really only care about whether it's raining or not. They might use that to either debug it or to present it down the road, but they don't necessarily put that into the loop with the simulation. So in our case, again, this is simulation where you want the physics to go and you want to run the physics. You never want player input when you're doing a physical simulation because you don't want any input other than sort of the initial conditions of the situation. So it's a different beast entirely to do a real simulation in terms of what you're trying to do with it. Okay, so kind of the core of any of this activity is understanding the most basic form of physics, which is that two things don't interpenetrate each other, right? We have a solid nature. It's also known as the normal force. It's the force that keeps us from putting our hand through the desk when we lean on it, or walking through a door rather than having to open the door to walk through the doorway, right? We don't actually walk through doors. And so this kind of overlap here is incorrect, and we want to solve for that. So our first case is trying to find these overlaps when they happen and then correct them. Okay? So probably the most straightforward one that we will see is this version here in 2D, where we really go down to the frame buffer and recall that the frame buffer looks something like this. This is actually what our screen looks like. We have RGB elements when we zoom in on the monitor, and each of these is encoded by the frame buffer in memory in the video card, and we send data in there. But to understand that the things you're seeing on your screen are made up of pixels, right? And so when we can go down all the way to the pixels, and here's a very zoomed in view so you can see the tiny little squares that represent the hand overlapping the face. And we can simply count the pixels, or look at the pixels in both images and see which of those pixels overlap. And so when what we're looking at is a small enough number of pixels, this is fairly reasonable compute time, right? So we might be looking at a couple hundred, or a couple, maybe even 1,000 pixels here in total on the screen, and it's fine. We could count those and we could figure out all of the places that were overlapping in order to detect that overlap. And so that's very precise. This was actually, in many cases, done in the early days of 2D simulation, 2D platformers, to do pixel perfect collision detection, and it's still done in some cases to make the requirement of pixel perfect jumps and making sure that your character lands exactly and down to the wire. But it's not the best, and it's usually in many cases it's probably not necessary because the player isn't going to notice, and they might also feel cheated if they really do only hit a single pixel and suddenly that counts for or against them in some way. But of course, in the cases where it works for you, when you land on that single pixel that counts for an edge in a tile on a jump that you just barely made, it feels pretty good. But you can get the same kind of effect with the bounding box. So sort of the next level of collision detection up is to put bounding boxes around things, because it's very, very trivial to compute the overlap of a bounding box. So all we really need to do is take the minimum and maximum along one axis, right? And we say, is the minimum between these two, or is the maximum between these two, right? So the maximum is sort of between the two min and max of the orange, or the minimum is between the min and max of the green. And so we can compare that with actually only a total of 4 comparison checks. I will let you work that out on your own. You can try to look at that and try to understand, what am I needing to compare, and come up with it. So it's 4 comparisons per axis, and then there's another 4 comparison. So it's 4 comparisons for the x-axis and another 4 comparisons for the y-axis. And if we determine that we are overlapping in both axes, so we do need to overlap in both axes. If we're say overlapping in the x-axis, but we're actually not in the y, that means that our orange box is down here somewhere, right? So it's maybe over here rather than overlapping the y. So we have to overlap in all 3 axes, and we have to check all 3, or 2 in this case, but it extends easily to 3. And very quickly we can determine whether or not those 2 boxes are overlapping. So it's a very quality check. Sometimes we will layer this, and always we will kind of layer most of our checks with a sphere check, right? So sphere is, if you imagine drawing a circle around this where it's a perfect circle with a single radius, it tends to be larger than the box, right? So especially where our characters are sort of tall and narrow or slender, we can represent them in a box better. But if we were to draw a sphere around this, then really to check a sphere or circle is only one check, right? So you just need to compare the distances between the two points, the center of the circles, and then whether or not their radii are less than the distance, right? Or the sum of the radius. So the sum of the radius is either less than the distance or greater. If it's less than the distance, then they're not overlapping. If it's greater than the distance, then they are overlapping. And so a sphere check is even faster, but so we will layer those and say, first let's do a sphere check, and then we'll do a bounding box check. And then sometimes if we still want to be pixel precise, we could go in and then do a pixel check in order to layer those and make sure that we're not doing a pixel check every frame, right? So if we did actually have, say, 1,000 pixels that we need to worry about, then maybe it's not worth trying to do that every single frame. So we can layer that, but often it's worth stopping just at the bounding box because it's a reasonable level of accuracy. So one of the problems we run into is that you can already see that with this green box here. The boxes aren't necessarily, so if we've got an axis aligned bounding box, it's not tight, right? And so so it gets larger than necessary. And then potentially if we try to have the box follow the character and the character rotates for some reason, or any number of things can happen to change the size, we suddenly need to deal with these orientation differences, right? So we're no longer in this simple space of axis aligned bounding boxes and being able to check these things, but we can be a little bit more efficient. So rather than having to draw the orange square much larger than necessary and having a lot of wasted space down here, if you imagine a box taking shape around this character that's rotated, we could rotate the box with him and then see how well we can do from there. So this is kind of the next level of overlap complexity, and we do something like an inside-outside test. So in this case we might say, let's look at each of the vertices of the green box here and see if any of those are inside the orange box. And so in this case we've got this one's outside, right? And so we see that we hit an even number of surfaces, right? An even number of edges. So if we cast a ray out and intersect, and try to intersect that ray with all of the edges of the box, we note that we hit 2 of them and that we don't hit the other 2. So again, if we hit an even number, then we're outside of the box because we've gone in and then we've gone back out. whereas here we hit an odd number and we've only gone out. Right, so the even odd thing actually works fairly well for any kind of shape, and so it could actually work with concave shapes as well. So a concave shape is one which sort of curves back on itself and maybe has like a little indent in it. And so these kinds of indents still pass the even odd test. Okay, so the inside-outside test is fairly straightforward. Let's take a look at the way that the comparison actually works. So this is just a sketch of the radix line intersection, and I bring this up mostly to look at the math and talk through it a little bit, but I don't expect you to be very comfortable with it. Just to kind of understand in broad strokes what's happening and why it's still fairly straightforward. It's not as easy as the bounding box check, the AABB check, so axis line bounding box check. But it's worth understanding the levels that we're talking about here so that you understand when to use each and how they operate, right? Rather than maybe need to fully understand them so you can implement yourself. You're not necessarily going to need to implement it. Okay, certainly not for Unreal, and not for this class. So, so all that to sort of couch, try not to be too worried about the math, but do try to understand it to some degree so that you feel comfortable understanding what's happening underneath. So if we imagine, so we have the Q represents our ray, and the P represents the line, right? Or it's really the end point of this line, and the Q represents the end point of the ray. And what we're looking at is Q is a vector in space. It's a 3-vector. You can think of it's actually a position in space, but you can think of a position in space as being a vector which is pointing from 0 to my position, right? So if I imagine the 0, 0, 0 position in space, then every position is a vector in its own right. It's a 3-vector, but it's really a special kind of vector that means I'm in a specific location, whereas most vectors are meant to really represent a direction. And so in the case of S, we have a direction and we have a length to it, right? So it's going to move us out. Really, S is a direction, an infinite direction, because we're a ray and rays go infinitely in one direction, right? And so what we might do is think of S as being simply unit length, and then we're going to multiply any point along that ray by some, the S by some amount, some scaling amount, and it's going to move us along this ray, right? So if we move to 1, we're just going to move 1 unit away from Q. We move to 2, we're 2 units away, so you can think of that as 2S, or 3 units away, we're now 3Q plus 3S, and so on, and we move through space that way. Now P is a line, which means it has an endpoint over here, which we'll call something like, well, I would use R, but we've already used it over here, so I'm going to call it L. So we start with P, let's call it P0, and then P1 over here would be our endpoint. But really, we can think of lines as also being rays, or really infinite, and we just need to know that at certain distances we're going to stop, because we're not going to move past that line, right? And so the entire point of what we're trying to find here is that we can think of starting at P and moving along the line, and we can think of starting at Q and moving along the line, and we want to find out the point at which these two intersect. And every line, because they're all infinite lengths, will cross at some point. It ends up being a quadratic equation. And what we do is we say P plus TR, so at some distance T, we're going to, along the R, so we can think of the R direction as going this way. Again, the S direction is going this way. So P plus TR and Q plus mu S gives us a distance, and what we want to solve for essentially are T and U, right, or mu, I think it's U. So again, we know what P is, we know the direction that P is going to travel along its line, we know what Q is, and we know the direction that S is traveling, and what we need to do is solve for these, and so we set them equal to each other. We try to figure out how T and U are related, and it ends up being oh no, it's not a quadratic, but it does solve to a single value, right? However, it could solve to an imaginary number for either, that they're not actually equal. And it could also, otherwise it will solve to a fixed number. So I'm going to ask you to think about it for a moment, and then I'm going to tell you the answer. Under what condition might we get an invalid answer, or an imaginary number out of our result? And the answer is that when they're parallel, right? So two lines that are parallel will never meet. But any other situation, we will get a result. It's just that we might get a negative number, right? So although we're expecting to go along this direction with u, turns out if the line is behind us, we'll get a negative u. Or in the alternative case, if we're p and we're trying to find a line along here, but it turns out our intersection point was back here, we'll get a negative t. But in both cases, we'll actually get an answer that's correct. There's only one case where we'll get a completely invalid answer. And I encourage you, if you are comfortable with math, to work through this, to understand how you would actually solve this, and to understand that it actually breaks down to a fairly straightforward solution given all of the things that we know ahead of time. And so given all of this information, we can very quickly check each of these lines and against each of these rays and determine how many collisions we have against the four lines in question here. Now the other thing I will mention is we do know the length of this line, and actually we could potentially know the length of the ray as well. We don't necessarily need to go infinitely, but it doesn't matter in this case. If you know the length of the line, then maybe in both cases you might say, well, if I've got a ray and I've got a line and I know that I want to hit that line exactly, the negative numbers mean that I'm not overlapping in this sense, right? So if I'm looking at something like this and the line is behind me, then I know I haven't hit it because it's way back here. And so because I was casting my ray in this direction, I didn't hit the line over here with my ray. And so again, the other sort of case that we don't care about is if I'm starting my P here and I walk down to the line and my actual intersection is way down here, well past P1. So again, we call this sort of the P0 marker here and a P2 marker here. If the result that I come up with is way past it, then I can ignore that one as well because I'm not intersecting. And so that's really the only extra trickiness that we have to do here. We can say, in this case, infinite lines can always intersect and parallel lines will never intersect and so on. But in our case, we actually do know the endpoints of our line and the starting point of our rays, and so things like negative numbers actually can be ignored because they aren't overlaps, and so we not return those results. So they don't add extra complexity, they just add a few extra branches to our checking to decide whether or not we're actually overlapping. But overall, the math remains fairly straightforward, and just a few mathematical operations, and then we find the result that we're looking for. And again, I encourage you to look that up, but if you are to work it out for yourselves, if you are savvy in the math and interested in that domain, and if you're not, at least understand that the math is fairly straightforward. So you might be wondering how we decide what direction to cast a ray, and it comes down to this, that we actually don't cast the rays arbitrarily, or at least in most cases we're not going to cast the rays arbitrarily. We want to know if we want to know if we're intersecting our two boxes. And so what we looked at was a ideal case where we have like this perfect pixel inside here, but here's sort of this really sort of the opposite of ideal, unideal case of two boxes overlapping in the absolute worst possible condition. So if we take a vertex and start looking out in any arbitrary direction, this vertex is not, it looks like all of these vertices are outside the box, right? And so that's kind of a problem when we run into this. And so what would we do? And it turns out that we actually don't use the inside-outside test for the lines. We use it sort of in that kind of way, but we really use a line-to-line intersection. So it's a similar kind of process. Certainly the inside-outside test is a reasonable one to check and works very well if you want to find out, say, if you've clicked a point in space anywhere, you could send a ray out in any direction to decide whether or not you've clicked inside, right? So if I imagine my mouse trying to test if it's inside some shape, I could actually use that point. For the case of lines, we end up using the same ray to line intersection, except now we really just use line to line intersection. And what we're looking for is whether or not we are crossing lines at all. So if I compare this line and I compare any of the lines over here, or all the lines, I find that I cross multiple lines, right? And so what we're really looking at now is essentially a surface, right? So if we imagine this as the surface in 2D, we're comparing all of the surface elements, all the edges that make up the outside of this box, and against all the edges that make up the outside of this box. And if any of our edges overlap, by essentially looking at edge-to-edge comparison, that intersect, any of our edges intersect, then we can say we're having an intersection, right? Now we still have a question of how far we are intersecting, and we'll see that that's important for the physics. But at least in the first case, we can check whether or not we're overlapping at all, and then go into how far we're overlapped as sort of a second pass. So it's really a small extension of the ray to line intersection here, just to say it's a line to line intersection. Both of them have a limit, and as long as I check every line here against every line over here, and so it really ends up being 8 checks, right? Or say, let's see, 16 checks. So it's 4 times 4 checks, which still isn't too bad. Again, the math is pretty straightforward, but that's really what we're looking for. Any intersection from this line to any line on this one is considered a real check at that point. We can say some part of our box is inside when we do a check like that. So we can extend this, right? So I said this kind of represents a surface, an exterior surface. The edges for a box, of course, represent kind of a basic exterior surface. And again, if we go all the way back and look at this, we're really trying to represent our shape in some simplistic form here. So we can generalize that a little bit. So now that all we really care about is understanding the outside surface, rather than looking at Sonic, we could say, well, and now I don't want to do a box, right? Maybe I do want to try to get a little bit closer, so I'll create a convex hole. So what I could do is start looking at this and drawing these outside points, right? So you see these small purple points here that kind of represent the extreme edges as I move around it, and there's a variety of convex holing algorithms. They're reasonably quick in their way, and in some cases you can pre-compute them, especially if you've got sort of known shapes. You might be able to pre-compute your convex holes, but they can be somewhat heady to compute, especially if things are changing often. But for this instance, we'll say it's pretty reasonable. Rather than 4 edges, now we have 1, 2, 3, 4, 5, 6, 7 edges, which doesn't extend it too much. If we imagine some other character that's at least as complicated as Sonic, we might have like 49 comparisons, edge-to-edge comparisons. But it's not getting overly complicated yet. So 2D convex holes are pretty reasonable. And in fact, you'll find that the collision systems in 2D games often continue to be fairly complicated, and people will do some pretty interesting physics because it ends up being simple enough that you can continue, even with some of these complex convex shapes that you need to come up with. You can still kind of figure out the inside-outside check or the edge-to-edge check or all that that's necessary with 2D shapes. However, 3D suddenly ends up quite a bit more complicated, right? So here's an example of pretty detailed shape, right? So Sonic is pretty detailed in pixel shape, but we can still get a convex hole that's fairly reasonable. We can get some lines here that still represent the shape fairly well, and we feel comfortable with that, right? However, if we look at, say, even this low poly case, if we're really looking at the surface elements, what we're talking about is now the surface element is this square here or this square here, right? Each of these quads represents the surface of our whole shape. Now we could, by comparison, look at each of these pixels along the edge as a full surface, and of course Sonic does have quite a few of those. So there's several hundred or maybe even several thousand that make up the outside edge of Sonic, and so by that means seeing 9,000 just to represent the head isn't actually that bad. So it's one thing to do the face-to-face comparison, and we're okay with that, but in the understanding that we might have to compare 9,000 cases times 9,000 cases, that's not so good, right? That's like saying we have to go all the way back to the pixel-to-pixel comparison every time. And so that's not necessarily a good idea, but it gets worse. So unfortunately, convex holes in 3D are not as easy to compute as they are in 2D. They end up with a lot of degenerate cases. So these kinds of narrow, thin triangles here are degenerate cases. And of course the convex holes, because they end up being very weirdly shaped, they're maybe okay, but we still end up with quite a few extra shapes here that probably aren't necessary. And we could hand roll a shape But then we run into problems with animation, right? So if we were to hand craft a shape around this, that's okay too. But then we need to handle it for every animation, and as we will see, animation itself is kind of saving us a lot of complexity, but it also could hurt us if we had to, undo that complexity by finding our convex shapes. So maybe the rule of thumb is this is all well and good when you're in the 2D world, but once you get into 3D, we kind of need to fall back to somewhere in the middle again. So what do? Well, we kind of go back to our standard shapes again. So we go back to boxes or spheres or maybe capsules. So capsules are really just, or cylinders. Cylinders and capsules are kind of a special case or special hybrid, you can imagine, of sort of a box and a sphere, right? So they're sort of circular in one axis, but they're square in another axis, right? So at least one axis it's sort of a square-like shape, or at the ends with a capsule we have these little round shapes. So if we're past the end, we'll check a radius here. Inside we're more like a boxy shape, and with the cylinder along this axis we'll be checking the radius versus the length, right? But along this axis we'll be checking like we do with a box. So we come back and we actually end up doing sort of our edge to edge and length and distance checks that we were seeing all before, but we're doing this in 3D for box to box comparisons. And so we simplify, but we do have a number of boxes, right? So it turns out that a lot of the cases, these kinds of primitives, either spheres or capsules or boxes, are trivial enough that we can afford to use many of them, right? So a box has, so the 2D box that we saw before had 16 checks to compare box to box. A 3D check, we're talking 6 surfaces, has 36 checks. So it didn't actually increase that much. We went from 16 to 36, right? So remember, a cube-like or a brick-like shape has 6 sides to it. 6 total. So we don't care about edges now. We're talking about the sort of outside surface, which means when we go to 3D, our outside surface is the flat edge or the flat planes, right? The quads. And so for a box, 3D box, we've got 6 sides, and so to do a box-to-box comparison, we do 36 checks. So it's more, but it's not so bad. And so if we had, say, 20-ish boxes that we were comparing, then we're not doing too bad, right? And so we get advanced edge. So this is actually looking at, I think, CSGO and comparing the old version where they did square boxes, and they actually had some capsules to get a little bit better accuracy because capsules felt, I guess they felt like those were getting more accuracy. In our case, the difference is fairly negligible unless you're trying to get really precise. So if you're looking into that, you might go investigate why they chose to do that. But for our purposes, just understanding that looking at these kinds of convex shapes that represent segments of the body is a much better solution than trying to use convex holes or even just doing a surface-to-surface check, especially if we're trying to do a very high poly model that we're comparing against. So we find that this actually happens in 2D as well. So they still don't want to do, so this is kind of the Street Fighter case, right? So we've got Street Fighter, King of Fighters, all these kind of 2D fighting games. They don't want the level of inaccuracy that you would get by drawing a box around this guy, right? However, and they don't really want the inaccuracy that they get from a convex hole either, and they still don't want to do the full pixel-to-pixel comparison because that's just too much, right? And so rather than going all the way down to that, they will still just use the box-to-box. And so they will use bounding boxes that represent the full shape, and they might even find that in real time by dividing up certain chunks and breaking it down. It's a specialized sort of algorithm they might do there. But then they will compare these shapes. They might also draw them over the sprites because the sprites are kind of a fixed set. But the point is that by comparing these boxes in 2D against, say, whoever this guy's kicking, we can decide pretty accurately whether or not he did successfully kick or hit the other guy. Rather than the sort of larger box that we might run into. You also get to divide it up and say, did I collide with the non-interactive part, right? Did I collide with his body over here, or did I actually collide with his leg, which is the part that's trying to do the attack in this case? The last thing I'll mention is that there's a lot more to the full collision system. This is kind of just the introductory level. There's also this notion of collision spaces, and this now becomes sort of the next level up. So we talked about layering our colliders. So we could say, at the basic 2D level, we might compare a sphere first to decide whether or not we're even reasonably close, and then we'll do the box collision check, and then we'll go down and do a pixel-to-pixel check, right, if we really want to get accurate. Well, the collision space is almost taking it a step up and saying, rather than just looking at two objects and deciding whether or not their radii are near each other, let's put every object into the full space and try to decide where are objects reasonably close to each other. Right? So there's kind of two main spaces for that. One is what's known as quad tree or oct tree deconstruction. That's where we break up the space into, in this case it's 2D deconstruction. We break up the space into quads, and where we have sort of the shape of things that are interesting. So we look at, say this sphere, or the edge of the sphere, or sorry, the edge of the circle is the most interesting, so we'll break up our space as small as we can here. So where we have a lot of people, we would break up our space more, and where we have no people, or where we know that it's empty space, then we just leave it as all empty space and say, let's ignore this whole section. And so what that does is lets you kind of focus on the parts you care about by breaking it further and further down where necessary, and leave out large portions where you know that there's no reason to check at all, right? So if we know that nobody's inside this space, we can ignore this entire region. Whereas here, we know that there is, say, two people inside the space. There's the inside of the sphere and the outside of the sphere. And so we need to do our more detailed comparison inside that check. Over here is what's known as a KD tree. This is a way of breaking up the space so you can find the nearest neighbors. And so this is there's other uses for KD trees, but one of the basic ones is to find the nearest neighbors. And so you could say, if I'm a person in space, I want to find out who my 3 or 4 nearest neighbors are, and those are the ones that I'm going to check immediately to figure out whether or not I'm actually colliding. So then I'll do my higher detailed check of the box-to-box check, but I can at least start and say, who's closest to me before I need to check every single person in this space, right? So these spaces let you sort of ignore, and so when you're dealing with, say, an MMO or just a game with, say, thousands of colliders in it, you don't necessarily want to have to compare your complete hitbox set of 49 comparisons or 36 comparisons times 20 times 1,000 every single frame to figure out if any of these guys are hitting. And so this is kind of our next and last level that lets us look at the whole scene and break up the whole scene and understand possible connections here. So again, this is just to let you familiarize with it, understand that these things are pretty efficient, as efficient as it can be, but you can help it along by understanding where the limitations are. Don't put a lot of people very close together. Don't put a lot of colliders very close together. You will get performance issues. Don't don't have your nearest neighbors all close together. Make sure you can break up your scenes so that the collision spaces work.